Hi, I am Daphney-Stavroula Zois, a Ph.D. candidate in the Ming Hsieh Department of Electrical Engineering at USC, and my research focus is on the joint problem of tracking and resource allocation in heterogeneous sensor networks. My motivation stems from the developing area of ambient intelligence, where sensing devices of different capabilities and usage codes form heterogeneous communication networks so as to track time-evolving and unknown phenomena. The successfulness of the associated application heavily relies on the efficient and holistic management of such resources, and in order to be able to do that, you should be able to answer effectively the question, how can we efficiently track a time-varying unknown process by adaptively exploiting the available heterogeneous resources. So this is the question that I'm trying to answer in my thesis. As a case study, I have looked at the problem of physical activity detection in wireless body area networks, W-bands for short. So here at USC we have built a W-band that consists of accelerometers and heart rate monitors and a fusion center which is a Nokia N95 cell phone. The communication between the sensors and the cell phone is done via the Bluetooth protocol, and the W-band is worn by an individual who is performing a set of physical activities such as standing, running, etc. During the real deployment of such a system, we realized that if the cell phone is continuously receiving samples from other sensors in its sensor network, its battery is not more than 4 hours. So in contrast to traditional sensor networks where we optimize energy resources at the sensor level, here we are interested in optimizing energy resources at the phone level. At the same time, we had to face the problem of multimodal sensing in the sense that certain sensors could better discriminate between specific activity sets. For example, you see here that if we use data both from the accelerometer and the heart rate monitor, we are able to detect between the 4 activities: lie, stand, walk, and run. However, the sensors have different usage costs. So the question that we answered is which sensor should we listen to, when, and for how long? And what we proposed is a partially observable Markov decision process formulation where the state of the individual is modeled as a Markov chain, and the measurement vectors that are generated by the sensors are used to update a belief we have on the underlying state of the individual, which then is used as an indicator to activate and deactivate each of the sensors at each time step. We also developed, based on this formulation, we also developed sensor selection strategies, and namely we derived the optimal sensor selection strategy using dynamic programming principles that saves energy and detects the individual's activity. At the same time, we proposed 3 approximation schemes that had much lower complexity than the optimal solution. In addition, evaluating the performance of the algorithm, all the algorithms on real data, we showed that we can achieve, compared to state-of-the-art approaches, energy gains as high as 68% with 99% detection accuracy, and in fact the performance of the approximate schemes were near optimal. Finally, in all cases we used very few resources, namely very few samples. Last but not least, I have been looking at the scalability aspect of my problem in the sense that how can I address state space explosion in the case when multiple state types such as emotion or time or location are considered apart from physical states. Towards this direction, I have developed new state estimation techniques. For example, I have developed Kalman-like estimators for discrete time finite state Markov chains observed via Gaussian measurements, and have also derived the optimal policy to minimize the associated state estimation error. Currently, I'm looking on how I can accelerate detection and control tasks in such problems by exploiting the underlying structure of the state space along with finding concise representations of the related processes. Thank you.